In this video, we will be discussing the periodic trends in the ionization energies for atoms. First, there are two different ways that we can make ions. Ions are produced either by adding electrons to or removing electrons from an atom. Electron affinity is a measure of the atom's ability to gain an electron. So that would be its affinity for electrons. Ionization energy, on the other hand, is the measure of the amount of energy that is needed to remove an electron from an atom. The ease with which an ionization occurs can be estimated based on the location of the element on the periodic table. The ionization energy, again, is the minimum amount of energy needed to remove an electron from an atom or ion in the gas phase. It is an endothermic process. Whenever you are removing an electron, you have to put energy in to overcome the attractive force between the electron and its nucleus. The valence electrons are going to be the easiest to remove, so they will have the lowest ionization energy. And the reason that the valence are the easiest to remove is they are the outermost electrons, so they are starting out the furthest away from the nucleus. Now there are different ionization energies that we will be referring to, and these relate to how many electrons we have removed from the atom already. The first ionization energy is the amount of energy that it takes to remove an electron from a neutral atom. So the first ionization energy corresponds to the removal of the first electron from our atom in the gas phase. All atoms will have a first ionization energy. The general reaction for this process is we have whatever particular atom we're interested in. We add some energy to it, our ionization energy, and then we get the atom as a cation having a positive 1 charge, and we're removing 1 electron. So the first ionization energy is taking the neutral atom, applying some energy, getting the cation with a +1 charge, and removing the first electron. Once we have removed the first electron, from most atoms we can remove a second. The one that we can't do this for is for a hydrogen atom, and that's because it only has 1 electron. For all other atoms, there will be a second ionization energy because they have more than 1 electron. The second ionization energy is the amount of energy that is required to remove the next electron from our atom. So we've removed our first electron to give us our cation, our +1 cation, and then we apply an additional amount of energy to remove the next electron. So commonly the second ionization energy would be labeled as IE for ionization energy, and then with a subscript 2. So the 2 here denotes that we are removing the second electron. So to remove the second electron, you first have to get rid of the first electron. So we've removed the first electron to get the +1 cation, apply our additional amount of energy, which is our second ionization energy, and then we now have our cation with a +2 charge and our next electron coming off. So to go from the neutral to the 2+ cation, we first have to apply the first ionization energy to remove the first electron. Then we will take that cation, apply an additional amount of energy, the second ionization energy, to remove the second electron. We can then remove the third, fourth, fifth, sixth, depending on if the atom already has 3, 4, 5, or 6 additional electrons. In our discussion, we will first look at the trends in the first ionization energies, and then we will look at the trends for second and sequential ionizations to see what types of trends we can spot. So the first trend is for the first ionization energy. A graph of the first ionization energy versus the atomic number looks like this. What you'll notice is that for a given group or column of the periodic table, as you go down the periodic table, so like helium, neon, argon, krypton, xenon, the first ionization energy goes down. As you go to the right, so hydrogen to helium or lithium to neon, in general, it goes up. There are a couple exceptions to this that we will cover why those occur. But in general, as you go down the periodic table, the ionization energy decreases, and as you go from left to right, it increases. There are a couple things that are leading to these trends. First, there is a larger effective nuclear charge on the electron that is being removed. So it takes more energy to remove it. What you are trying to overcome when you're trying to ionize an atom is you're trying to pull the electron away from the nucleus. So if the effective nuclear charge is higher, there is a greater attractive force pulling the electron in, and you will have to fight that higher attractive force in order to remove the electron. So as you go left to right, because the effective nuclear charge increases, the ionization energy will also increase. As you go down the periodic table, the electron becomes easier to remove, partially because the effective nuclear charge decreases as you go down, but also because the electron is further away from the nucleus, making it easier to remove. So the further the electron's most probable location is, remembering of course that the orbitals are probability distributions, and as you go down the periodic table, those probability distributions get larger. So the further the electron's most probable location is from the nucleus, the less energy it takes to remove. So as you go down the periodic table, it gets easier to remove that first electron from an atom. So the general trend is that the first ionization energy, the amount of energy required to remove the first electron, decreases as you go down a group. And this is because the valence electron is further away from the nucleus, and because the charge-charge interaction decreases as the distance increases. If you're increasing the distance, that attractive force is less, making it easier to remove the electron. Also, the first ionization energy generally increases as you go across the period, and this is because of the increasing effective nuclear charge as you go from left to right across the periodic table. Looking at this graphical representation of the first ionization energies, you will notice that the noble gases have very high ionization energies compared to the rest of the atoms, and that the alkali and alkali earth metals have the lowest ionization energy. What this means is that it's very difficult to remove an electron from a noble gas, and much easier to remove an electron from either your alkali or your alkali earth metals. So to again summarize, the first ionization energy generally decreases as we go down a column, family, or group in the periodic table because the electron in the outermost principal shell are increasingly further away from the positively charged nucleus and are therefore less tightly held. The first ionization energy increases as we move across a row or period from left to right in the periodic table because the electron in the outermost principal shell will experience a greater effective nuclear charge. This covers the general trend for the first ionization energy of main group elements, which as you go across a period, a row of the periodic table, going from left to right, the ionization energy increases. However, from the previous graphs, you might have noticed that there are exceptions to the general trend. Thankfully, there is a reason for those exceptions, and that reason is the same one as we saw when we were looking at the electron configurations for why there was a difference in the electron configurations of things like chromium and copper, being that half-filled and fully filled sublevels are more stable than if they are partially filled, and that breaking up a fully half or fully filled subshell requires some additional energy. If we compare the first ionization energies of something like beryllium and boron, the first ionization energy for beryllium is actually higher than for boron, even though boron is to the right of beryllium. The reason for this is in the case of beryllium, when you are removing your first electron, you are removing it from a filled subshell. You have all of your 2s's are being filled, and so you have to pay an additional energy penalty for removing that electron and breaking up the fully filled subshell. In the case of boron, the electron that you're removing is from a subshell that only has one electron in it, and is not either fully filled or fully half filled. Each one of these boxes is not the same, and so you don't have to pay that additional energy penalty to remove that electron. Let's look at another one. Again, in general, your first ionization energy should increase as you go from left to right across a period. However, if we compare nitrogen to oxygen, the electron configuration for nitrogen, if we're looking at an orbital diagram, you'll notice that the nitrogen has a fully half-filled subshell for the p orbitals. To go and remove the first electron would be removing your electron here and giving you a nitrogen plus. That nitrogen plus would have a non-half-filled subshell. So going from a fully half-filled subshell to a partially filled subshell, this difference requires a bit more energy than if we were removing an electron from perhaps like the nitrogen plus, this type of an arrangement. So to ionize nitrogen, you have to break up a half-filled subshell, which costs that extra energy. In the case of oxygen, you have this configuration for your orbital diagram, in which the electron that you will be removing is occupying a box that is different from the others. So to remove this electron, you actually end up with an atom that has a fully half-filled subshell, which makes it actually easier to remove this electron because you end up with the very stable electron configuration that looks like this. So as a result, in terms of the first ionization energies of nitrogen compared to oxygen, even though oxygen is to the right of nitrogen, it's easier to remove its first electron than it is to remove the first electron of nitrogen. Once you remove the first electron, for most atoms, you can continue and remove a second, third, and successive electrons. The ease with which you can remove the electrons depends on the number of valence electrons that the element has. Removing each successive electron will cost more energy. The reason for this is as we remove electrons, the effective nuclear charge increases and the radius decreases. So the outer electrons are becoming closer and closer to the nucleus, and because the charge-charge interaction increases with decreasing radius, it becomes more difficult to remove the outer electron. So you have a shrinkage in size of the atom due to having more protons than electrons. Essentially, your effective nuclear charge goes up. The outer electrons, because they are closer to the nucleus, are therefore harder to remove. So when we are looking at the second, third, fourth, and fifth ionization energies, what you will notice is that in general there will be a regular increase in the energy for each successive valence electron. Often the increase in energy required for each successive electron will be a similar value. So the first one might take 2,000 kilojoules to remove, then the next one could be 4,100. The one after that would be 6,300. With each successive electron, there was an increase in about 2,000 kilojoules of energy. However, what you will notice is that there will be a large increase in the energy when you start removing the core electrons. Essentially, when you break the noble gas configuration, there is a very large energy bump required for removing the electron that breaks a noble gas configuration. If we look at sodium and magnesium, for sodium, it is an alkali metal, so it is in the first group or first column of the periodic table. The first electron is fairly easy to remove. It takes only 496 kilojoules per mole. The next electron, which would break a noble gas configuration, requires 4,560. That is a very large jump between the first electron and the second electron. The third electron will always require more than the second, but the jump going from first to second is more than going from the second to the third. There's a difference of about 4,000 kilojoules per mole difference in the first ionization energy versus the second, whereas going from the second to the third, the difference is only about 2,400 for the difference in energy between the second ionization and the third. For magnesium, you'll notice the first and second one, each time you pull an electron off, it requires an additional roughly 700 kilojoules per mole for the first and second. The third ionization energy is 7,730 kilojoules per mole. So this is a very large jump in the increase between each one of the successive ionization energies. So going from the first to the second, each new one required an additional 700. But going from the second to the third, the difference is about 6,000. So we can use this information to determine which atom we're working with by looking for the big jump in our ionization energies. So let's say we didn't know that we were working with sodium and magnesium. Based on these large jumps, we could tell that this is something that's coming from the first group or column in the periodic table because of this large jump that happens when removing the second electron. Similarly, we could tell that this data here, is coming from something in the second group of the periodic table because removing the third electron would have this very large increase in energy, which should correlate to breaking a noble gas configuration. So if we extend this and look to all of our elements that are in the third period or third row of the periodic table, what you'll notice is that each one has a large jump in its ionization energy. For sodium, it's between the first and the second electron, so removing the second electron requires a lot of energy. For magnesium, it's the third electron that requires a lot of energy. For aluminum, it's the fourth. For silicon, it's the fifth. So what we can do is, if we didn't know which element we were working with, but we knew which row of the periodic table we were working with, we could look at the ionization energies, look for the large jump, and then count backwards to determine which element we were working with. So let's say you had some data that suggested that the sixth ionization energy was very large as compared to the fifth, fourth, and third. So essentially, the difference between the first and the second is about 1,000. The second to the third is again about 1,000. The third to the fourth, this one's a little bit bigger at 2,000. The fourth to the fifth is 2,300. And then the fifth to the sixth, the difference here is about 16,000. What that would tell you is that removing that sixth electron, because the change in how much the energy of the successive ionization energies was much larger for that sixth electron, that would tell you that the sixth electron, removing the sixth one, broke the noble gas configuration. You started to remove core electrons, which requires a lot of energy to do. So what you could do is count back from the noble gas 5 spots, and that would give you the atom that you were working with, because it was the sixth one that broke the noble gas configuration. So the sixth one would take us, for example, to fluorine. So going 5 in the other direction would tell us which element we were working with, right? 5 electrons got us to the noble gas configuration, so we can count backwards. Going from neon to sodium is 1, then magnesium is 2, aluminum is 3, silicon is 4, and phosphorus is 5. So if it took 5 electrons to get to the noble gas configuration, which we would know because the sixth electron is the one that broke the noble gas configuration, we could tell that we were working with phosphorus.